Germany, 1911. A meteorologist named Alfred Wegener was browsing through some books when something caught his eye. A list of identical plant and animal fossils that had been found on opposite sides of the Atlantic Ocean. Wegener was intrigued. How could the same species have gotten from one part of the world to another? He examined the eastern coast of South America and the western coast of Africa and was struck how the shapes of the two coastlines might fit together. The more he looked, the more links he found. Species of land mammals in East Africa also inhabited the island of Madagascar. How did that happen? Did the animals evolve in both places at once? Or did they somehow cross from one land to the other, swimming hundreds of miles across the Indian Ocean? And then Wegener saw it all clearly. He realized that all the continents in the world had once formed a giant single landmass that he called Pangaea, from the Greek Pangaea, meaning all earth. It was in Pangaea that the plants and animals found on opposite sides of the world had once shared the same home. Then, over hundreds of millions of years, Pangaea had split apart, and its jigsaw pieces had drifted to their present locations. Wegener called his theory Continental Drift. Wegener wasn't the first scientist to speculate that the Earth had once been dominated by a supercontinent, but he was the first to pull together all the evidence and make a strong case for it. Unfortunately, his peers weren't very receptive. There was no mechanism to explain how the continents might plow through the oceans. Continental drift was just too incredible to believe. As a result, his discovery was largely ignored.
So in 1912, Alfred Wegener suggested that all land masses were once this big supercontinent called Pangaea, but he didn't have any mechanism or any reason why this actually happened, why everything started out as one landmass and then separated away. But what he did have, he did have evidence of the big landmass. He just didn't know how it got to what we have today with all the land masses separated. He called this continental drift. He said that the continents drifted away from each other, but he couldn't explain it. He couldn't figure out how that happened. He didn't have enough information, but he did have some evidence. One major piece of evidence was that all the continents seemed to fit together like a big puzzle piece, which is something we'll look at in just a second. Another thing he noticed is that fossils of land animals, which had no right being separated by thousands of miles of ocean, as well as geographic formations like mountain ridges, they seem to kind of line up if you put the pieces or the separate parts of the world together, parts of land masses together. So the first evidence is that the South America and Africa seem to fit together like puzzle pieces. And if you look at them, they look to fit pretty well, actually. South America fits nicely into Africa, and they fit together as if they were just one landmass. And you may notice that if you look at North America as well as the west coast of Africa here, that North America, with Florida being down here and then Maine up here, it looks like it fits the curve of Africa as well. Another piece of evidence is that you had land animals that were that you have fossil records on continents that were far, far away from each other. Now, the fossil records from a certain level down matched between the two land masses, between South America and Africa. However, above that point, it seemed like the two fossil records diverged, which means that it seemed that both of them were together, the land masses were together for a while, that had the same animals on them, but then they separated and then the animals evolved their own separate ways from that point forward. And that was another piece of evidence that these land masses were together at some point in time. Also, if you look at the mountain ranges that are on the west coast, the east coast of North America, as well as the north part of Europe and Asia, you can see that these mountain ranges here seem to look like they connect. So if you put the pieces together, then you can see that they're all a part of the same mountain range. And this was another piece of evidence that Alfred Wegener used in order to say that, well, these land masses actually used to be together because of this. Now, Alfred Wegener, he had a lot of evidence. He had a lot more evidence than what I'm showing right here. But these are the major highlights of the piece of evidence that he presented to say that the continents moved away from each other. So over the past 200 million years, he said that that Pangaea would look like this with all of the continents together. But he didn't have as accurate of information what we have nowadays. If we look at 200 million years in the past, it would probably look more like this. Now, it's not one landmass because you got a couple pieces that are out here, but essentially it's one huge landmass because of the better reconstruction, the better evidence that we have these days with more precise measurements. So this shows the breakup of Pangaea. It looks like it started out as one big landmass, and in that landmass, each plate moved away to its current location over the past 200 million years.
World War II. German U-boats were on the prowl. To track them, the Allied forces developed new sonar methods, and scientists were enlisted to help survey the ocean floor. When the United States entered the war, Harry Hess was a geology professor at Princeton University. But he also happened to be a Navy reservist, so it wasn't long before he found himself in command of an attack transport ship in the Pacific. To help maneuver when coming in for a beach landing, Hess's ship was equipped with a depth sounder. Now, still being a geologist at heart, he used the sounder to measure the depth of the ocean floor whenever his ship was out to sea. Now, what he discovered startled him. Until the Second World War, most scientists imagined the bottom of the ocean looked like this: flat, lined with nothing but sediment. But about 2 miles beneath the waves of the Pacific Ocean, Harry Hess discovered something else entirely. Mountains like these here in California, with deep canyons and trenches, hundreds of high peaks that we now believe were once active volcanoes, and all of this at the bottom of the Pacific Ocean. Surprisingly, though, the discovery of the Pacific mountain range is not what makes Harry Hess part of our Great 100. Now, we'll get to that in a minute. To understand where all this is headed, I'd like to skip ahead to another event that set the geology world buzzing. For years, oceanographers surveying the Atlantic Ocean had taken sonar readings that indicated there was something down there, something big. In 1953, they found out what it was: a 12,000-mile-long mountain range. They called it the Mid-Atlantic Ridge.
The reason it's so great.
To fill us in, I paid a visit to Neil Driscoll, a geologist at the Scripps Institution of Oceanography.
One of the big discoveries that was made was that there was this ridge of underwater volcanoes that stood high above the seafloor.
How high is a mountain in the middle of the Atlantic?
The average seafloor depths are on the order of about 4,000 to 5,000 meters. The mid-ocean ridge sits up at about 2,500 meters. So they sit about 2.5 kilometers on average higher than the surrounding seafloor that's shown here in the deep blue colors.
So that's over a mile high.
Yes.
And that's where Harry Hess comes back into the story. Analyzing core samples and sonar readings from around the Mid-Atlantic Ridge, Hess made an astonishing discovery, a phenomenon almost beyond comprehension. The age of the Atlantic Ocean floor, he determined, was progressively older the further it moved away from the ridge. Harry Hess had discovered that the seafloor was spreading. He concluded that molten rock was being forced up from inside the Earth at the ridge, where it then formed into new crust on the ocean floor. Gradually, it was pushed away on either side as more molten rock continued pushing up from behind it. Hess called his great discovery seafloor spreading.
Harry Hess was in a position that he could bring it all together. Things were spreading apart and new Earth was being generated. But if you did this for long enough, the Earth should grow. and it doesn't.
The Earth doesn't get any bigger.
No. Harry appreciated the fact that if new Earth was being generated in one area, they have to be consumed or recycled in another area.
The process that recycles the crust of the spreading ocean floor back inside the Earth is called subduction. But as our next great discovery revealed, it's all part of a much larger process, perhaps the most powerful force on the face of the Earth.
That the earthquakes
Hess's discovery that the seafloor was spreading rescued Alfred Wegener's idea of Pangea from obscurity. Now there was a geological mechanism to explain continental drift. That's simple.
once you hear it, it sounds great.
It does sound great. By the 1960s, both ideas were synthesized into a single theory, the science of plate tectonics. A great discovery that revealed just how complex and dynamic our planet is. Several groups of scientists had concluded that not only is the Earth's crust moving, but the surface of the planet is broken into large, interconnected plates. These plates are constantly in motion, floating on a layer of molten rock in the Earth's mantle. It seems fantastic. I mean, it seems just too crazy. How could the whole world be sliding around? I can see where people were skeptical.
That's right. But it's the rates that your fingernails grow.
That's not very fast. I don't feel a thing.
That's right.
Yeah.
But cumulatively, it's huge. So here's the thing: is geologic timescales is what makes this so important. Because if you think of it over a year, you move a few centimeters. If you think over millions of years, you're moving kilometers. About 250 million years ago, all the plates were together in Pangea, and they're moving apart, and they will come back together again.
Why do they move back together?
Because the Pacific Ocean right now has subduction all around it, and the plate is actually being consumed and recycled, where the Atlantic Ocean is spreading without much subduction. So the Atlantic Ocean is going to grow, the Pacific Ocean is going to close, and then we'll start getting closer to Asia and closing up the Pacific Ocean.
It's crazy.
It's pretty great.
Crazy.
And once you hear it, it's hard to imagine geologists not believing in it. So once the theory and the mechanism, that was the important contribution.
Because no one would believe it till they had it.
That's right. So the plates are spreading, they're not plowing.
The understanding of plate tectonics has given scientists new insights into the changing face of our planet. A dynamic example of some of those changes can be seen here on the California coastline, where two of the Earth's largest plates, the Pacific and the North American, collide.
There's a number of results, but one, we get volcanoes where the plates are subducted back into the Earth. These volcanoes happen because the plate that gets subducted releases water, and this water lowers the melting temperature of the overriding plate and makes it easier, and we get volcanism.
So that's where you get Mount Whitney, Mount Shasta.
Things like this, absolutely. The Andes are a perfect example of these type of volcanoes. Other places you get the mid-ocean ridges. You get pieces of the seafloor that are 1 to 2 kilometers higher than the surrounding seafloor. These are underwater volcanic chains that stretch the length of these ocean basins. Other places you get large strike-slip faults.
So what's a strike-slip fault?
A strike-slip is when the plates move by one another, okay? And they don't do it without kinks and twists. And so where the kinks and twists are, there can be places that lock.
Yeah.
And then they release, and they release quickly with a lot of energy or momentum.
Tipping over buildings and so on.
Causing a lot of shaking, yes.
But without earthquakes, you never would have found all this stuff, right?
Earthquakes are really important because they've allowed us to define the plate geometries. They've allowed us to define the boundaries.
So what about volcanoes?
Before volcanoes light off, a lot of times there's pre-eruption seismic activity.
Shaking.
Yes. As the magma ascends to the surface, it causes stress, and the stress is released.
Do you see evidence of plate tectonics right here?
Yes. What we're looking at in the sea cliffs, these sediments were deposited about 500 meters below the sea level, and they've been uplifted. So here, we're looking at plate tectonics in our own backyard.